Hello, Rajaram sir.
Hello. Hello.
Yes, sir. ಇನ್ನೊಂದು 2-3 ನಿಮಿಷ. Sir, Rajaram sir, ನಿಮ್ಮ ಕ್ಯಾಮೆರಾ ಆನ್ ಮಾಡಿ ಸರ್. Rajaram sir, can you hear me?
One ನಿಮಿಷ sir, one ನಿಮಿಷ.
Okay. Yeah. ಇನ್ನೊಂದು 5 ನಿಮಿಷ ರಮೇಶ್ ಸರ್ ಇಂಟ್ರೊಡಕ್ಷನ್ ಕೊಡ್ತಾರೆ, ಆನಂತರ ನಾವು ಪ್ರೆಸೆಂಟೇಷನ್ ಕಂಟಿನ್ಯೂ ಮಾಡೋಣ ಸರ್.
Okay sir, okay.
Yeah, he is there online.
ಸರ್ ನಮಸ್ಕಾರ.
ಸರ್ ನಮಸ್ತೆ ಸರ್. ನಮಸ್ತೆ. ಚೆನ್ನಾಗಿದ್ದೀರಾ ಸರ್?
ನಾವು ಹೇಗಿದ್ದೀವಿ?
ಆಡಿಯನ್ಸ್ ಬಂದು PU ಹುಡುಗರಲ್ವ ಸರ್? ಓಕೆ ಓಕೆ ಸರ್.
ಮೆಜಾರಿಟಿ PU ಹುಡುಗರು, ಮತ್ತೆ ನಮ್ಮ KST ಮೆಂಬರ್ಸ್ ಕೆಲವರು ಜಾಯ್ನ್ ಆಗ್ತಾರೆ.
ಸರಿ ಸರ್, ಸರಿ.
ಪ್ರೊಫೆಸರ್ಸ್ ಮತ್ತೆ ಇವರು ಚಾನ್ಸಲರ್ಸ್ ಎಲ್ಲ.
ಓಕೆ ಸರ್.
So we have mixed audience. Most of the people will join in the YouTube because they find difficult to join in the Cisco. That is the reason. Sir. ರಮೇಶ್ ಸರ್ ಸ್ಟಾರ್ಟ್ ಮಾಡೋಣ ಸರ್, ಟೈಮ್ ಆಗಿದೆ.
Good afternoon, everybody. First of all, welcome to Dr. R Rajarama Krishna, resource expert for today's. Speaking on physics of transparent materials. Now I welcome all the new students teaching faculty, also my colleagues to this webinar. Before actually going for talk, let me give a brief introduction on the achievements of Dr. R Rajarama Krishna. Dr. Rajarama Krishna is working as a coordinator and head of the PG Studies and Research in Physics at the National College, Jayanagar, Bangalore. Completed his master's from Bangalore University in the year 2007. He was selected for PhD program from Bangalore University in the year 2010. During his PhD program, he was selected as JRF from Department of Atomic Energy. Major research project, and he completed the project and PhD year 2014. Supervision of academician Professor Rajan V. Ambekar. Later, during his doctoral program, he was also invited as a research scientist to Lehigh University, Pennsylvania, United States in the year 2012, 2013, supervision of Professor Himanshu Jain. After completing his PhD in 2014, he joined as assistant professor in physics, Department of Postgraduate Studies and Research in Physics at the National College, Jayanagar. He was also sanctioned sabbatical leave for 2 years from the National College, pursue postdoc fellowship program offered by reputed National Research Council of Thailand to Center of Excellence in Glass Science Technology and Material Sciences, supervision of the scientist. He is an expert in glass science technology, in solid state physics and material sciences. His research interests involve nanoparticles embedded in oxide glasses and research related to photoluminescence, nonlinear optical properties, and synchrotron structural analysis of glasses. Dr. Ramakrishna has 10 years of research and teaching experience. Of his research work is listed as top cited article in Radiation Physics and Chemistry from 2022 date. Noteworthy achievement. Congratulations, Doctor. He has more than 84 national peer-reviewed journal articles published with more than 1,000 citations, having H index of 18 and I-10 index of 33. Nearly 32 postgraduate students and 3 PhD students and 2 undergraduate students. And with this little background about his achievement, I request Dr. Rajarama Krishna to deliver a talk on physics of transparent materials. This over to you, Doctor, for your talk.
Thank you, sir. Thank you, Dr. M. Ramesh, sir. So I'm honored to deliver my talk on physics of transparent materials on this auspicious occasion from KSTA, organized by KSTA. So shall I share my PPT, sir?
Please share.
Yeah. Okay. So good afternoon to everybody. The topic of my title will be on physics of transparent materials. So organized by KSTA, I should congratulate them for organizing this particular event and providing me an opportunity to do this particular talk. So let me start from my content, what I'm going to speak today. So I'll be discussing about opaque materials, of how the materials cannot or could not able to transmit light. So transparent materials, translucent materials, eye perception of light, glasses, how glass is being prepared, and properties of light. So the entire contents will be mainly focused on PU student, pre-university students. So based on pre-university students, the contents have been derived to this particular talk. So first of all, why can't we see light through the walls, or why can't we see the light through the walls or woods? So what makes or what limits the light to not to pass through from the walls? So why do we see that the light passes through the glasses, and why can't the light pass through the walls? So what is the phenomena behind this particular talk, or what is the phenomena behind this particular concept? So in general, if I would like to pose you a question, why can't we see the light? Can anybody say why the light cannot be passed through the walls or woods? Is there anyone who can give the answer? Hello? So the simple reason why the light cannot travel or light cannot pass is a property called opaque. So the material being an opaque property, the light cannot pass through the particular walls or woods, or even it could be a metal or anything which is painted, or anything which can be having a the colored pigments. But when it compared to the glasses, they do transmit the light, and we consider to be a concept called transparent. So that is the reason behind why an opaque materials cannot transmit light, whereas the transparent material do transmit light through them. So almost everything what we see in this particular case do consider this particular entire thing. Almost everything shows the opaqueness, like wood, metal sheets, it could be colored plastics. So anything as such, if you see into these consideration, every phenomena do show a concept called a opaque concept, which means that light cannot pass through them. And what is the importance of transparent and translucent? So these are the materials which are being prepared in National College, Jayanagar. So we can see here in case of a glasses, they do transmit light through them, and also they have certain colored glasses which can transmit light through them with different wavelengths, so which I am going to discuss later. And here is the phenomena where you can see a wood can be made translucent material by treating them with the sodium hydroxide. A lignin polymer can be removed, or cellulose can be removed from this particular wood, which can make it as a translucent material. We can also make it as a transparent material by proper treatment of sodium hydroxide. So we call these materials as a translucent materials. And also these are the natural wood fiber composites. By treating the natural wood fiber composite with proper sodium hydroxide, we can make all these materials as a translucent. So but where you can see here, these are the glasses which are transparent. So there are two things of property, transparent, translucent, which we're going to discuss in further. So one is opaqueness, transparent and translucent. So opaque do not allow light, transparent do allow light, but translucent do show a partial, the light can be allowed only partially. Now, can opaqueness vary with nanostructures? The question is here, how the opaqueness can be differentiated, or can we break the opaqueness by minimizing their structure? So to explain this particular term, I would like to show you a demonstration. Now look at this particular demonstration. I do show the 10 centimeter hand where the color of and texture changes when we go deep down to 1 centimeter. So the 10 centimeter texture deep down to 1 centimeter do look in different manner. The color also changes. Whereas if I go in deep, down to 1 millimeter, the same texture changes, the color changes, and the where you can see a difference in their particular structure. 100 micron. So as we go down deep down, so the changeover can be seen visibly. 10 microns, 1 micron, 100 nanometers. So 10 microns is the WBC, and RBC, the DNA, 10 nanometers. And at last is the 1 nanometer, which looks like an atomic structure. So nanostructure is different from macro, size, color and shape. So all these size, shape, color defines the transmission of light. Now, why do the water, when we look into the molecules or atoms, how does these atoms or molecules do transmit light through them? So to understand this, we need to know the light spectrum. In general, we do have a longer wavelength to shorter wavelength region, but what we are interested here is visible region. The visible region is what we need to understand. So in the visible region, we look from VIB-GIR. So VIB-GIR is the region which we are going to study in this particular case. So starting from violet to red. So how does this VIB-GIR or violet to red visible region do show an important characteristics for this particular matter? So to understand this, let me go back to the concept. So the water, how the water molecule transmit light in a UV radiation or UV light. So to understand this, let me go to the demonstration part so that I can show you the, here is the demonstration. So if I use the visible light, if I use the water molecule H2O, and if you look into the visible light, if I switch on the light, so the water molecule do not show anything. I mean, it passes the light through it. Whereas if I use the ultraviolet also, they do show similar phenomena. So UV and visible do show the same phenomena. Whereas if I use the IR light, you can see the vibration of this particular molecule. So two hydrogen atoms start vibrating with the IR rays, and microwave also, it can rotate. So IR waves rotates the molecule. Infrared makes the vibration, whereas visible and ultraviolet do not show any such characteristics, which means the visible light and ultraviolet can easily pass through this particular light. So having said that, having understood about this particular phenomena, so let me go back to the let me sorry sorry for the disturbance. I mean, the PowerPoint is not working, it's not responding. Let me hello. Hello. Sir, am I audible? Hello. Yeah. So as we saw the water transmittance, how the water transmit light in a visible radiation, how the water transmits in the UV radiation. So based on the light phenomena, or how the light travels in these molecules depends or defines their transmissions of their particular light. So even water acts as a transparent material when a light is being passed through it. So as we have observed all these phenomena in the day-to-day life activities. So when it comes to the opaque objects, how the absorption takes place. In general, opaque objects absorb light completely. When the absorption, when you look into this particular case, so the light absorbs completely in this particular phenomena. So no light is transmitted in this particular case, in case of an absorption. Whereas in case of an transparent objects, the light transmit through the glasses. So the transmission of light can be seen in these particular consideration. So what happens in transparent objects? So they undergo absorption, they undergo refraction, they undergo reflection, they also undergo the scattering phenomena based on the structure of that particular material. So structure defines very important phenomena of the particular object. So if the object is a transparent, then the structure of that particular object defines all these phenomena, so where it can dominate in future. So when it comes to translucent objects, the light can partially transmit. So you can see here, so the light is not as much as what we see. Complete light cannot be transmitted, so due to the translucent material. So again, these translucent materials can also undergo refraction, reflection, and scattering phenomena. So when it comes to transparent objects and translucent objects, so we can see that these are the transparent objects where we can see clean water, plastic bottle, air, glass. So these are certain examples which comes under the transparent concept objects. Whereas in case of a translucent objects, so milky glass, butter paper, and plastic sheets, these are the examples which comes under the translucent objects, where the light passes partially. Now, when it comes to the perception of light to the eye, so generally human eye sees or understands how the what color of light is being taken. Let me go back to the uh, 1 second. Let me go back to the animation part. Yeah. Now look at the look into the light. So when red photons are illuminated onto the optic nerve or eyes, so the a human see only the red color. So the color again changes when we switch on the green light. So the color of that particular visualization of that particular light will be varied through the optic nerve, because two photons or two different wavelengths are illuminated to that particular optic nerve, or what we call it as an eyeball. So when I switch on the blue light or blue photon, so RGB, we see white color. So all the three colors or three lights makes the color to become white. So the perception of light is very, very important when it comes to the human eye. So how the eye receives when we consider to this particular case. So let me go back to this concept. So on that particular concept, so how the eye perceives the light photons is also a very important criteria, because as we see that the transparency of that particular material, cell membrane, is also one of the huge, plays a vital role to understand what sort of a color or what sort of a energy it is being illuminated or absorbed. So having said that, so similar to the optic nerve or optic lens, what we have as an eyeball, so we need to understand the optics based on the glasses, made of the glasses. So now these are the one which transmits light. Also, these are the objects which can scatter light, refract light, reflect light. So all these phenomena can be understood based only when we prepare a glass. So these glasses are also one of the important criteria where how these glasses can be made, and why do we prepare the glass, and what is the use of the glass. So why windows are made of a glass? The simple question for this, why do we use a window glass? To restrict the light, UV light, which is harmful for the eyes. So to restrict the UV light which are coming from sun rays, so we use the glasses. And also these glasses are prepared by soda ash, limestone, sand. So when we use stoichiometry, appropriate amount of soda ash, limestone, and sand, and keep it in the 1600-degree furnace or more than 1000-degree furnace, these melt can be quenched and prepared these glasses. So these are the glasses which are prepared in our laboratory. So where we can see that these are the different materials, oxides, which are mixed in a particular stoichiometry ratio and heated to a high temperature furnace, in the high temperature furnace. As I said, so these glasses, once we prepared these glasses, limits the UV radiation, so that which protects from harmful UV light. Now, the work which we have been followed in our lab, that is NCJ lab, so has a collaboration or collaborative work with the Bengaluru University, also collaborated with the CEGM lab Thailand, and also we have a Sinclair lab which is collaborated from Lehigh University, USA, and Indonesia, Indo lab, which is collaborator. So these are the 4 laboratories which are all right now, 5 laboratories which are right now collaborated to our national college to prepare these glasses to understand the phenomena of transparency and the physics behind the transparency. And also we are going to understand the properties of light also, because light is the one which defines the transparency of that particular material. Anyway, now let us discuss about the physics behind this glass, how the glass is being formed, what are the ingredients which may require, or how does it being understood. Initially, we need to take a proper stoichiometry ratios of different oxides, as we saw in case of previously we saw that soda ash, limestone, sand. So we need to take the soda ash, limestone and sand, which is sodium carbonate, calcium carbonate and silicon dioxide. Even even if I melt myself inside the furnace, I also become a glass. So even my body is also consists of all these chemicals. Mainly my body is consists of a phosphate, that is your bone. So when I melt myself inside the furnace, I can also become a glass. So that is the beauty of preparing glasses in the laboratory. But it's just a joke for that. But generally the body is consisting of phosphate material, so we can make ourselves as a glass part. And in many Asian countries like Thailand and other parts of Philippines, they do have these customs. Once when the elders die, they prepare glass out of their ashes, so they keep it as a gemstone for in their ring. That is also a custom which custom and ritual which they follow in afterlife. So anyway, as we see in case of these when we take a appropriate stoichiometry oxides and weigh them in a microbalance and use it in a porcelain crucible or platinum crucible, keep it in the furnace for 800 to 1500 degrees Celsius, these oxides what we have used will start melting because the temperature is very high. So once these oxides are melted, they have to be quenched, or they have to be poured in the brass plate, preheated brass plate around 350 degrees Celsius. Once these melt is preheated, quenched, they become glasses. So these glasses will be cut into proper shape, polished, and you can see here these are the glasses, and then we measure it for density as well as refractive index. So we are going to discuss about the refractive index also in the later section. So that is an important property of a glass or a transparent material as such. So the story of glass formation goes like this. So to understand the story of glass formation, we need 2 important criteria. One is volume, which is under y-axis, and the second one is temperature, which is under x-axis. So x-axis is temperature, volume is under y-axis. Now just imagine that when I start heat, let me take a liquid water and I start boiling the water. What we see is the water evaporates, which means the volume of that particular which we have taken in a vessel start decreasing as the temperature increases. So that is the concept we have to understand here. So once these oxides, once these oxides which are taken in the crucible is been heated, so when we quench it or when we bring down to the room temperature, that is the physics which we are going to discuss here. So the glass formation also discuss about the high temperature physics. So this entire phenomena occurs in the high temperature regime. So by looking at these diagram, volume versus temperature diagram, we need to see understand 3 important criteria. 1, melting temperature, which is represented as Ts. 2, Tg, which is represented as Tg, that is glass transition temperature. And 3, viscosity. So viscosity is the property of which resists the flow of liquid. So viscosity is a resistance in which we observe in case of liquid conditions. So based on all the phenomena which we have seen, so we're going to understand this particular thing. We usually start making glass by melting that particular oxides, as I said. So these oxides is being melted. The region what we see is a highlighted region, shows the volume of material which increases as the heat is increased. So the rate of increase remains the same until the material reaches the Ts. the melting temperature, which we call it as a Ts. And once the at the temperature, there will be a sudden rise in their volume. You can see the volume is getting increased. So which means there is a change in their phase, or phase transformation occurs at this particular point B to A at this on this range, shaded region. So here the solid material becomes a liquid material. In this region, the solid, whatever the solid which we have taken as a oxides or powder, which becomes a liquid. So, and this region is the phase transformation region or phase transition region. Beyond this region, the blue region, what we see is the melt. So that particular solid becomes a liquid. So here it will be a solid. So here the phase transformation occurs, and at the blue yellow shaded region, at the blue region, so the entire solid, the phase transition solid becomes a liquid region. So it gets melted at this particular point where the pressure is very, very large. So now upon cooling them, once we heated, and now we have to bring it down, because we need to heat up to 1500 degrees Celsius, which melts the oxides, and then we need to bring back the temperature to the room temperature from 1500 to room temperature or 300 degrees Celsius, which is a which we call it as a rapid quench technique. So hence the conventional method of preparing glasses are called melt quench technique. So this highlighted blue region is the one where the volume of that particular melt at different temperatures will be seen. Now upon cooling that particular melt or liquid, because these oxides become liquid, and we need to cool it down. So while cooling down, they turn it into crystal when it traces back from A to B and B to C, B to G, or if it travels, it bypasses that particular crystalline phase, then it becomes glass. So the entire phenomena here is to make sure that it should not bypass, it should not go through the same path where it started. Initially, from where it started, it should not come back to the same path. If we can bypass this particular path, then only we can prepare the glass out of this particular oxides. Otherwise, these oxides becomes crystal. So upon cooling at Ts, at melting temperature, it can become, or it can turn into crystal, or it can begin to turn into glass. There are two possibilities. Hence I have shown 1 and 2. 1 is the pathway for crystal, 2 is the pathway for glass. So we need to make sure that the melt should pass through in this second pathway, then only glass can be prepared. If it is quickly, or if it is cooled quickly enough, then only it becomes glass. So we cannot cool them very slowly. If it cools down very slowly, then it can turn back to the same path and becomes crystal. So hence it has to be rapidly quenched or rapidly cooled, that particular melt, which is around 1500 degrees. So 1500 degree melt should be rapidly quenched to 300 degree within no fraction of second. So then only glasses can be prepared. So the Ts, what we see here is the highlighted in the red, which is the important point which can transfer from 1 to 2 or 2 to 1, glass to crystal, crystal to glass. So that is the turning point where the crystal can become a glass, or glass can become a crystal. And once this particular region bypasses the crystalline phase from A to C, when it travels from A to C, this particular region is called as supercooled liquid region, or where the viscosity will be very, very less. So the resistance of the flow of resistance for that particular liquid will be very, very, very less. So flow of resistance will be very, very large, so that the liquid will become high viscous part in this case. So we consider this particular region as a supercooled liquid region, and this region is very, very crucial for a glass to be prepared. So beyond this supercooled liquid region, that is point C, beyond point C, they become glasses. So this particular point is the liquid phase. The phase transformation will happen or occur beyond C to become a solid, and that solid becomes a glass. So as the supercooled liquid region becomes cooler, the viscosity becomes greater, and then this particular viscosity resists them to prepare or to become as a they prepare as a solid. So hence they become a glass. So in this particular point, there is another turning point at point C where they can show different TG, or what we call glass transition temperatures. So the glasses can show 2 different or 3 different glass transition temperature based on their crystalline phase or based on their structure. So TG is the glass transition temperature as the temperature becomes hard enough to consider as a solid. So beyond this supercooled liquid region. So this is the story of a glass, how the glass is being formed. I mean, the physics behind the glass. So one has to very carefully observe their pathway where the glass or where the melt transfer from liquid to solid through this particular pathway too. So then only a glass can be prepared. Now, when we consider the glasses, as we can observe the band structures of these glasses. So when it comes to the band theory of solids, so generally these in case of a conductors, the valence band and conduction band will overlap, whereas in case of a semiconductors, so the valence band and conduction band has a very low or limitation. The difference between the distance between valence band and conduction band will be less, whereas in case of an insulator, the energy gap or the distance between the valence band and conduction band will be larger. So what decides this glass? Glass can vary between insulator and semiconductor. It can be tuned or it can be tailored their properties between semiconductor to insulators, but not the conductors. But in general, glasses falls under the category of insulators. What do we mean by insulator? The light what we pass has to pass through this particular energy gap, which means they become transparent. Hence the glasses shows a transparency in their property. Why glasses show transparency? Because the energy gap between the valence band and conduction band is large. Hence they allow all the light to pass through this particular band. Hence they transmit complete light. Whereas when it comes to semiconducting materials, which is transparent materials, they do allow the light to pass through, but partial light will pass through this particular energy gap. Whereas in case of conductors, they reflect back. So they show a reflecting phenomena from the conductors. They cannot pass through the light. So this is the physics behind why the material cannot transmit light when it is considered in case of a metals, wood, or any other opaque consideration. So wood is an insulator still, even though wood is an insulator, they cannot pass the light. But whereas in case of a glass, they do pass. So why wood cannot pass? Again, there is a story behind that. We need to understand their cellulose structure, why the light cannot pass through the wood. So those are opaqueness, which has a different pigment, different color pigments. So which I am not going to discuss that particular wood property, but I am going to discuss about this solid material glass property. So where the structure is loosely bound together. Anyway, so how do we protect the light? Generally, the light can be protected by using the goggles, and many such experiments can be done, or experimental setups can be built in the laboratory to understand the different phenomena of light. One which comes the best comes under out of this application is laser or laser amplification of glasses and limiting applications of laser. So these two are important property when it comes to the concept. One which limits the light, the two which enhances the light. So these are the two important phenomena which we find. So when it comes to this particular property of light, we need to understand the reflection, refraction, and total internal reflection. So in this lecture, we only focus on these three important properties of light based on the pre-university syllabus is considered. I also can discuss about all these other property, but I hope I will complete these three within time. So if time persists, I can do all the other properties also, including certain derivations also for PU as per the PU board is considered. Now let me come to the reflected and refracted light. So I need to show reflected and reflected, right? So let me go back to the bending of light. So I hope you can see the animation picture. So here I have used the material what I have used is the air medium. So the refractive index is 1, and which is a top. You can see there is a plane which bifurcates the air medium and water medium. So below is the water medium, above is the air medium, and there is a light which I have been using, and there is a normal which passes in the particular phase. So when I switch on the light, so you can see that the how the refraction refraction occurs from air to water medium. So similarly, if I turn this particular part, if you look into the angle, if I make use of the angle, let me make use of the angle. So if I change the angle, you can see the refraction also is getting bent. So the bending of light can be easily understood by using this particular demonstration. So from air medium to, this is the rarer medium where the refractive index is 1, and this is the denser medium where the refractive index is 1.3, which is larger than the air. So where the index of refraction is 1.33 for water. So if I use the wave, you can see here how the wave nature can be used. If I change the refractive index from water to glass, you can see the bending of rays can be seen. So the angle of refraction decreases as I change from glass to water. So as I change from glass to water, the refraction increases. From water to glass, it decreases, and again it increases as I come to the air. And if I change the material medium which I am using, the source which I am using is, let me change from air to water. Look at the consideration. So how it is. So the medium is water, and the material used is glass. So by changing these property, we can see that how the bending of light can be seen. So this is the incident angle and this is the refracted angle. So incident angle and refracted angle, always the refracted angle will be less than the incident angle when it comes from the lower refractive index to higher refractive index, or what we call from rarer medium to denser medium. So if I change this particular phenomena to from denser to lower rarer, so exactly opposite will occur in case of this particular phenomena. So having said that, let me go back to my concept. So you can see here the ray refracts inside the water and reflects in the same medium, so air medium. So two different rays can be seen by illuminating the light on the plane. So this bending of light has two important phenomena what we are seeing in this particular condition or criteria. So one, in that case, we need to understand these two phenomena, reflection and refraction completely. So laws of reflection. So when it comes to laws of reflection, angle of reflection is equal to angle of incidence. When you look into this particular reflected ray, so the angle of incidence and angle of reflection is exactly same, not almost, exactly same. So to observe this particular criteria, let me use the angles. Let me now look at this. So when I use the angle of incidence is 45 degree, angle of reflection is also 45 degree. But whereas the refraction angle is less than the incident angle. So this is what we need to know in fact. So if I change the angle, you can see that the angle of reflection is also exactly same, whereas the refraction keeps on changing. So it could be, if I change the wavelength, it doesn't mean what wavelength I am using, but it all means what sort of a refracting surface I am using here. So if I change from air to water, so you can see the angle varies, especially the refraction angle. So from air to water, if I change, the angle of refraction is getting varied, whereas the incident angle and reflected angle do not vary. So that is the property which we need to understand from this particular concept. So the incident ray, the reflected ray, and the normal at the point of incident lies in the same plane. So this is the plane which we are seeing. So all these angles are incident ray, reflected ray, and the normal line. So all lie in the same plane, which is the law of reflection. So when we study the law of reflection, we need to make use of this particular phenomena. So everyone are familiar with reflection, where we see in front of a mirror, and we used to get how the light rays are traveled from incident angle and reflected angle. So there are two types of reflections, one regular reflection and diffuse reflection. So in a regular reflection, it occurs in a smooth surface. You can see in this particular picture. So if I have a smooth surface, then the reflection coming out from that particular surface will be called as a regular reflection. If I have a irregular surface or a diffuse surface, what we can call, so in such irregular rough surface, the reflection coming out from the rough surface is considered to be diffuse reflections. So both are similar to each other, but the diffuse will be in different angles, whereas the reflected ray will be in the exactly same. The angle of I is equal to angle of R, whereas in the diffuse reflection also the angle will be same, but the diffusing of that particular reflection can be easily pointed out or understood. When it comes to the law of refraction, so one, we saw that how the reflection occurs. Two, we need to understand the refracted ray or refraction. So when it comes to laws of refraction, the first law says that the incident ray, the refracted ray and the normal to the refracting surface at the point of incidence lie in the same plane. So in the plane, you can see this is the plane. The incident light, the refracted light and the normal light will lie on the same plane. So this is the first law of refraction. We do also have a second law of refraction, which we consider as a Snell's law of refraction. In case when it comes to the Snell's law of refraction, so we can see that the ratio of the sine of angle of incidence to that of the sine of angle of refraction is a constant for a given pair of a media and for a given pair of a wavelength also. So you can see that let me show you the Snell's law concept. So here is the angle. So when I keep on changing the angle, you can see the refraction angle is also changes. So let me use the air medium and the glass medium, because I'm discussing on the glass part. So if I change the angle of incidence, the refracting angle is also changing. So the medium what we are using is N1 here. N1 is equal to 1 for the air medium. So that is the refraction. And the medium what we see as the denser medium is the glass N2 is equal to 1.50, and the angle made by them is the one which decides the Snell's law. So N1 sine I, that is 1 into 65.7 degree, that is sine 65.7 degree, which will be equal to N2 1.50 into sine of 37.4 degree. So this Snell's law suggests that N1 sine I is equal to N2 sine R. This is the refracted angle and this is the incident angle. It doesn't depend on what light we are using, or we no need to go with respect to waves also. So we only depend on the ray of light, how the ray will be changing with respect to this particular phenomena. Having said that, so the law of refraction purely discuss about the Snell's law, how it can refract the light or how it can bend the light from the normal line or normal plane. So here is the what we have seen as a picture. So incident ray, refracted ray, and the angle made by them is very crucial for to understand this particular equation. So the Snell's law says N1 sine I is equal to N2 sine R, where generally we see that angles are very crucial. So if the incident ray starts from the denser medium and it exits to the rarer medium, then the angle made by the refracted angle will be larger than the incident angle. Whereas in case of an incident angle, if it starts from rarer medium, the angle will be large. If the same incident light starts from the denser medium, the angle will be less. That is the differentiation between these two components. If if light enters from rarer medium, the angle should be large. If light enters from denser medium, the angle should be less, because the density depends, or density do matters in this particular condition, air and glass. So based on the refraction, we need to understand the refractive index of the material, because refractive index of the material defines how much bend or how much restriction or resistance can a material show to the light or light photons to pass through that particular material or object. So in that case, we do have two concepts. One is absolute refractive index and relative refractive index. So absolute refractive index termed as N, relative refractive index is termed as 1N2. 1n2 is nothing but n2 by n1. That is the ratio between denser medium to that of rarer medium, or two different mediums in that case. When it comes to absolute refractive index, the ratio of the velocity of light in vacuum to the velocity of light in medium is called the absolute refractive index. So when it comes to velocity of light in vacuum and when it comes to velocity of light in medium, medium will be your glass, or it could be a plastic, or it could be a material which is considered to be a transparent. So any material which transmits light will show certain refractive index. So that is the velocity of light in the medium. So the difference between these two will provide you the absolute refractive index n. So whereas in case of a relative refractive index, we see that the medium, first medium to that of the second medium. So the ratio of the velocity of light in the first medium to that of the second medium with respect to the first medium will give you the relative refractive index. In both the cases, so these refractive index doesn't have any dimensions or units. So they do not show any units and dimensions. Then comes the concept of total internal reflection. All these phenomena are the properties of light: refraction, reflection, and total internal reflection, TIR. So these are the properties of light which we see in case of these criteria. So why do we study the property of light? Because to understand the transparency, or to understand the translucent, or to understand the opaqueness, we need to have a source, or we need to have a light, and that light will be coming from sun or tube light or bulb or LED, what we use. Unless and until there is no light in the universe, we cannot judge, or we cannot differentiate differentiate between the transparency and opaqueness. So light is being light being the source to judge between the transparent and opaque characteristics. So hence we have to understand, or understand the property of light. And when it comes to property of light, this is one such property which we need to understand, that is total internal reflection, TIR. When a light moves from denser medium to rarer medium, when it comes to total internal reflection, the light should be inside the denser medium, and then the refracted light should be in the rarer medium, which means the density of light, the source which we use should start from the high dense medium, that is denser medium. So always the incident light should start from the denser medium, and refracted light should go towards the rarer medium. Then only the TIR can occur. So when a light moves from a denser medium to rarer medium, it bends away from the normal. So this is the normal line. So when incident light incident on this particular normal, so you can see that the refracted light will move away from the normal. It won't move towards the normal, it move away from the normal. Whereas in case of refraction, what we see here is, here it is the rarer medium and this is the denser medium. So when the incident light is allowed to pass on fall on this particular normal line, so the refracted line move toward the normal line. So it bends towards the normal line when light moves from rarer medium to denser medium. Whereas in case of a TIR concept, the incident light is incidenting from the denser medium and moving towards the rarer medium. So hence the light, what we see as a refracted light, will move away from the normal. These are the two important phenomena which we see. When light enters from rarer, so the refracted light bend towards the normal. When light enters from denser, the refracted light move away from the normal. So based on these two phenomena, we differentiate the properties of light. So as the angle of incidence increases, the angle of reflection will also increases. At a particular angle of incidence, the angle of reflection becomes 90 degree, and this angle is called as critical angle or incidence of critical angle. So once the critical angle is achieved, then we consider to be a phenomena called total internal reflection. When incident angle becomes larger than the angle of critical angle, or then only the TIR phenomena will kick in or come into the picture. So this critical angle of is the angle of incidence for which the angle is greater than 90 degree. So that can occur only when it travels from denser to rarer medium. So the right side, the picture what you see in the right side is the one which shows the phenomena of TIR, the image. Now, when it comes to TIR, total internal reflection, we are supposed to understand critical angle, which already we have discussed. So now, can we apply to a regular shape of a body? Yes, we can apply to a irregular shape or bent shape also. It do not have any, it should not, it is not required that it should have a straight line or anything like as such. So we can have any shapes which can be seen. So as the light enters inside these material, you can see that once it hits the normal line, so it should obey the critical angle. It should it should accept the critical angle where incident angle should be greater than critical. Then only the light will move inside the plane. So such that the signal, the loss of the signal can be reduced. So TIR is the one property which reduces the signal loss when it comes to this particular concept. So based on this particular phenomenon part. So as I said, when a light ray moves from denser medium to rarer medium, and if the angle of incidence is greater than critical angle, light reflects into the same medium which is required, so that the signal loss can be reduced, and this phenomena is called as TIR, total internal reflection. So what are the property, I mean how do we prepare TIR? So these are the two important criteria which we have to follow. So denser medium to rarer, and angle should be greater. Now when it comes to application of TIR or application of total internal reflection, so the periscope, what we see, everybody would have seen this particular part. So there is a periscope which pops up and can be seen the ships in the surface of the sea. So how does this periscope work? On what basis this periscope work? The periscope consists of two prisms, so where the light will bend accordingly. So you can see that the bending of light can be seen in such a way that when a light enters to the prism 1, it exactly cut into 45 degree, that is incident angle and reflected angle will become same, that is I is equal to 45 and R is equal to 45. And then again in the we need to have another prism which again cuts the light into 45 to 45 degree. So here the critical angle of the glass, that is the glass which we are using, the critical angle of the glass is 42 degree. So we have to understand because of the critical angle of glass which is 42, the TIR is achieved. Otherwise we cannot have a periscope something like this. So we cannot make a periscope out of this with the prism and all, because it would have not achieved the critical angle. So being critical angle 42 degree, so if the incident angle is more than 42 degree, that is 45 here, so hence we can get a TIR condition. So the condition satisfies, hence the periscope can be considered as a TIR application in this case. Similarly, when it comes to binoculars, so application in TIR, in the binoculars can also be observed based on this particular TIR phenomena. So when a light passes through, we have two different prisms inside the binoculars. So when light enters the first prism, it undergoes to 45 degree reflection, again 45 degree reflection in two different phases, and again the light will be seen from the eyepiece. So this is again total internal reflection, because there is a exactly the 45 degree bending of light can be seen in the prism, which is greater than the critical angle of glass, which is 42 degree. Similarly, when it comes to Mirage, there is one more application when it comes to TIR, which is called Mirage. So on a hot summer days where the air seems to be pretty hot, or what we call it as hotter, so the ground becomes very hot, whereas at the height when we go towards the longitude, when we go from above ground to sky, so the sky seems to be cooler than the ground. So ground being a warmer and where we consider to be rarer medium, because the hot air is having a less refractive index compared to cool air. Cool air will be having more refractive index than the hot air. So hot air makes them a rarer medium, and cool air makes them the denser medium as it goes above. Due to this, we see that the light coming from the sun rays starts moving into different mediums, because it has to travel from cooler region to hotter region. So from which means denser medium to rarer medium, they do show different normals. You can see these are the different planes. As it cools down, I mean as it comes down to the ground level, so due to the hot air, so we see the light which travels through the eye seems to be mirage formed from the particular plane which we are seeing as a water. So generally mirage is considered to be a sort of at a different place, and when we are traveling in a desert region or when we are going in a road, so we see the watery image or liquid image which forms under the road or desert. So those watery image or kind of a pool image what we see is due to the TIR application, that is total internal reflections, where the light travels from denser medium to rarer medium. So it agrees the incident angle which is greater than the critical angle, and it shows the mirage medium. At a particular range, this particular line of sight becomes a straight line, hence a mirage is being seen or achieved for the observer. Similarly, when inside the sea, a fish will also undergo, or fish can also see the total internal reflection, or a human being or any particular person who are swimming inside the swimming pool or water do see the total internal reflection of the images. So even you can also have a refraction and TIR component from this particular concept. And one of the important application of TIR is the optical fiber. So nowadays we all see right now the internet what we are using is due to the optical fiber. The fastness of the internet can be improved by using the conventional wires to the optical fibers. So optical fiber made life easy than what we have seen a decade back in terms of technology wise, because these optical fiber, as I said earlier, so the loss of signal can be reduced such that the amplification of that particular light or signal can be boosted or increased. So to understand the optical fiber, here is the image which I have been taken from internet. So you can see that the optical fiber running all over the world through the sea, I mean underwater optical cables. So these are the underwater optical fiber cables which have been connecting the subcontinents, continent to subcontinents, and you can see from India. So here is the India. So here India to many parts of the country. So you can see Dubai, all these things. I mean from United States to you can see UK, Germany. So even towards the North Pacific Ocean from United States to China or Korea, Atlantic Ocean from United States to UK. So even you can see from Indian Ocean from India to Australia. So all these lines what you are seeing, all these lines are submarine or underwater optical fiber cable, where the internet, the capacity of internet fast, the internet facility is being done only in the submarine, I mean underwater, so that the loss of signal can be reduced. So here is the India. So underwater optical fiber in the India, we can see here these are the connection which are connecting to different parts of other countries in the underwater. Okay, so how does the optical fiber work? Because the application, when it comes to application part, we need to understand the physics behind the optical fiber. So we have two different medium A and medium B. When a light is passed through medium A, so you can see the wavelength something like this, and when it travels through the medium B, it reduces its wavelength. So the wavelength is large at medium A, but the wavelength is less at medium B, but the source is same. So keeping the source same, so we see different wavelengths. So this is the phenomena which we are supposed to take, or we are supposed to use for preparing on optical fiber. So in case of a medium A, what we see is the refractive index is less. In case of a medium B, the refractive index is high. So due to the refractive index is high, the medium B suffers, the wavelength becomes less. Whereas in case of medium A, the wavelength becomes larger. So making this particular phenomenon, understanding this particular property, we need to define the phenomena of light or bending of light. So you can see here the air medium, the refractive index is 1, the wavelength is larger, and in case of a water, the refractive index is 1.33, the wavelength is smaller. So here is the demonstration or picture which you can see refraction, reflection and TIR component. So refraction, bending of light, reflection within the same medium. So it cannot travel to the another medium in case of reflection. Reflection, so the light cannot travel in the next another medium, whereas refraction they do travel, but wherein in case of a TIR, complete reflection can be seen in case of a TIR condition. Now let us understand the optical fiber part. When it comes to optical fiber, they do have three important concepts. One is core, which is in the middle, and cladding, it is the outer layer of the core, which we call it as a cladding, and an insulator or insulation to protect these core and cladding. The core and the cladding is made of glasses and they are transparent in nature. They both are transparent. You can see here, these are the transparent core and cladding part. So again, they do show different concept, single mode fiber and multi mode fiber. So which I will not be discussing much on this particular topic, which is our research topic. I will not go in detail on that. So the core region is made of different component of glass, and cladding is made of different component of glass. So core is made of neodymium doped glass and cladding is made of samarium doped glasses for our consideration. In this particular case, we can make use of these particular two phenomena because these two glasses are being prepared in our laboratory. So hence I'll be discussing about these two part. So you can see here, this is the glasses which we have been prepared in our laboratory. Especially the samarium doped glasses which is being used for cladding. So as we see, the cladding and core they do possess different refractive index, and due to the refractive index, as we have seen in the earlier case, in general, so they do start, I mean to achieve TIR criteria, the light should travel from denser medium to rarer medium in general to get the total internal reflection, so that it will become, there is no loss in their signals. So that occurs in the core region, and cladding will be having a denser material, that is refractive index of the cladding will be lesser than the core medium, to understand. So in this case, the cladding is made of these glasses. We can see here at the normal light, you can see these are the pure transparent glass. When it is illuminated with UV light, they do show different color. So this coloring is due to different doping, that is samarium doping or something else. So doping we will discuss in the later part, but we need to understand how these glasses changes their color. So that is again a question of one more class. These glasses which I am discussing right now is being done in the National College, where we prepare the cladding part. We also prepare the core part also. So how the cladding can be understood based on the color segment, CIE color chromaticity diagram discuss about their colors. What we see here in the orange region, whatever, so they do change the color based on the mixing of these color. So when these glasses absorb light at different wavelength and emit at different wavelength, then these glasses do undergo to obtain a particular emitting of light, and that emitting of light emits at a particular region, that is you can see at this part, this case, that is orange. So for these glasses, the orange emission can be seen, and this orange emission glasses can be made use of as a cladding in the optical fibers, and they do also possess certain CCT, that is color coordinate temperature, which I will not be discussing in this lecture now. And I thank you. I thank Dr. A.M. Ramesh for providing the opportunity to deliver this particular talk. Hello.
Doctor, thank you very much for a very informative and scholarly talk.
Thank you, sir. Thank you.
Mix of transparent materials. Mr. Lobo, are there any questions? Lobo.
Sir.
Questions in your
ಕ್ವಶನ್ಸ್ ಸದ್ಯಕ್ಕೆ ಯಾವ್ದಿಲ್ಲ ಸರ್. ಸರ್ ಒಂದೇ ಕ್ವಶನ್ ಇದೆ.
One question. Yes, sir.
What about scattering of light when we pass light through water molecules?
Yeah, for that particular question, let me share the. Let me share the. Let me go back. Pawan, can you see this, Pawan? Am I sharing? No, I'm not sharing. Yeah. Pawan, can you see this particular image
Yeah, it's
Yes, sir. Yes.
simulation? Okay. So when it comes to the, now let me discuss about this part, scattering as, incident of light. Then I come to the scattering of light. So when I have a visible light, let me switch on to visible light, and I have taken carbon monoxide just for understanding. I'm applying the light to pass on this particular carbon monoxide. Nothing happens. Nitrogen, nothing. Oxygen, nothing. Water also, nothing happens. Whereas, but when I switch on to the infrared, it starts vibrating. You can see that the scissoring of the hydrogen molecule occurs. We call this as a scissoring or rocking. We call it as a hydrogen atoms rocks from towards left and right. When they do that, they produce certain energy. You can see the energy has been given out from that particular water molecule at infrared region. And same thing can be seen in microwave, which rotates. In microwave, it rotates. If you can see here, it rotates and it produces certain energy. So this is one such part to be understood, to understand our concept. So when it comes to scattering phenomena, as you can see, here is the scattering phenomena which I have been written actually in the transparent objects, because water comes under the transparent material. When it comes to scattering, the scattering phenomena has to occur based on the molecule which I have been seen. In this case, it is 2 hydrogen and 1 oxygen. So generally, the water molecule, when a light passes inside the water, so either it should reflect if the surface is good, still the water is still. 2, it should undergo refraction obviously, and then it can also have a TIR if the critical angle is achieved. When it comes to scattering, it should spread the light. The spreading of light can only be seen when the liquid or molecule water is being dispersed with milky or mud. When the dopant or when the impurities are added inside the material or in the liquid water, so they do show scattering phenomena. Unless and until there is no impurity in the water, the scattering phenomena will be less in general. So the scattering phenomena will be very less compared to clear water than the muddy water or impure water or any other particular water, like colloidals used in the water. So scattering is one such phenomena where we only see the light disperse from that particular region. So that is again the property of light only. So dispersion is again the property of light when where it travels from the object. The bending of light from the corner of the object. So generally, the scattering can be seen only when there is a impurity in the water molecule. So unless and until there is no impurity in the water, so the scattering will be very feeble compared to clear water.
Lobo. So, doctor, thank you very much.
Yes, sir.
Yes, sir.
Informative. The students may mail us questions. If they have any doubts, we'll be forwarding it to you. Please answer them and send back.
Okay, sir.
Once again, thank you very much from STA for your talk. I
Thank you,
also
sir. Thank you.
all the attendees. Monday morning again, one more talk on horticultural crops delivered by Dr. Ashok Alur, on the horticulture expert. Request all of you to kindly join at 30. Till then, thank you. Have a nice weekend.
Thank you, sir.
Bye. ಲೋಬೋ
ಸರ್
ಎಲ್ಲಿ ಇದ್ದೀಯಪ್ಪ ನೀನು?
ಸರ್ ಇಲ್ಲೇ ಇದ್ದೀನಿ ಸರ್. ಕ್ವಶನ್ಸ್ ಜಾಸ್ತಿ ಯಾವ್ದು ಇರ್ಲಿಲ್ಲ.
ಇನ್ಯಾರಾದ್ರೂ ಇದ್ದಾರ ಕ್ವಶನ್?
ಇಲ್ಲ 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 ಸರ್, ಯಾವ್ದು ಕ್ವಶನ್ ಇಲ್ಲ, ಅದೊಂದೇ ಕ್ವಶನ್ ಇತ್ತು.